Hey everyone, ready for another deep dive?
Always.
Well, today we're going to be looking at something seriously cool, like robots that move, like uh, like weightlifters or badminton players.
Oh, wow.
Yeah. So, strong but fast, but also smart about how they move.
Yeah, that's awesome. So much better than the big clunky robots we have now.
Exactly.
And probably safer too.
Yeah, definitely, and way more efficient. Okay, so the paper we're looking at today is called Planning with Purpose: Task-Specific Trajectory Optimization.
I love that title.
Yeah, me too. Planning with purpose. So what do you think that means in the context of robots?
Well, I think it means we're moving away from just getting a robot from point A to point B.
Yeah.
And now we're thinking about like the best way to move for whatever the robot is trying to do.
Okay, so instead of just programming a robot to be strong in general,
Right.
we program it to be strong for, like, the specific task.
Yeah, like, lifting a heavy box or something, or
Sure.
doing a perfect badminton swing.
Ooh, I like that example. So that's what we're going to be deep diving into today.
All right, let's do it.
Now, one thing that really jumped out at me at the beginning of this paper was how they took inspiration from, well, us.
Oh, interesting. Humans. Makes sense. We're pretty good at moving.
Right. Think about how you move differently when you lift something heavy versus when you're, I don't know, playing tennis.
Yeah. You use your body totally differently.
Exactly. And we do it without even thinking about it.
Yeah, it's amazing. I guess like our brains just automatically choose the best way to move for the situation.
Yeah, I guess that's what the researchers are trying to do with robots.
Totally. And they talk about this idea of redundant limbs.
Redundant limbs.
Yeah, basically it means we have more degrees of freedom than we strictly need.
Okay.
Like we can move our arms and legs in all sorts of ways, and that gives us the flexibility to choose the best pose or movement for the job.
Oh, I see. So it's like having a whole toolbox full of tools, and you choose the best one for the job.
Right. Exactly. That's a perfect analogy.
Nice. Okay, so we have these robots with all these degrees of freedom. How do they actually figure out the best way to move?
That is a great
Do
question.
they just, like, try a bunch of random movements and see what works?
No, not exactly. They use this cool concept called manipulability.
Manipulability.
Yeah, it's a way to analyze and visualize a robot's movement capabilities.
So, like, how well it can move in different directions.
Exactly. And also how effectively it can exert force in those directions.
Okay, so it's kind of like creating a movement profile for the robot.
Right. And they actually represent this visually using something called manipulability ellipses. Think of it like a robot's range of motion.
Okay, so, like, a big ellipse means the robot can move a lot in that direction.
Yeah,
And a small ellipse means it's, like, more restricted.
exactly. And there are two types of ellipses: velocity ellipses,
Cool.
which show how fast a robot can move in different directions,
Gotcha.
and then force ellipses, which show how much force it can exert.
Ooh, I like that. So it's like a visual representation of the robot's, like, strengths and weaknesses, but for movement.
Yes, I like that.
Okay, that makes sense. So, to put all of this to the test, they used a simulated 3-link robot arm, similar in structure to a human arm.
Nice.
Yeah.
Classic robot setup.
Right, so now we've got this virtual robot arm. What kind of stuff do they have it do?
Well, they focused on two very different types of movements. One that requires a lot of strength and one that requires a lot of speed, like comparing a weightlifter to a badminton player.
A weightlifting robot versus a badminton playing robot.
Yep.
This is getting exciting. Tell me more.
Okay, so strength versus speed.
Mm-hmm.
They wanted to design trajectories, like paths of motion that would make the robot excel at each one.
Gotcha. So, like, if we're programming this robot arm to be a weightlifter,
Right.
how would we do that?
Well, we'd use something called strong pose trajectories. Remember those manipulability ellipses?
Yeah, kind of. Remind me.
So for strength, you want to position the robot arm so that,
So it has the most power.
so that it's maximizing its force output.
Okay, so we'd be looking at the force ellipses,
Right.
and we'd want to find the poses where the ellipses are the biggest, right?
Exactly. Because that means the robot can exert the most force in those positions.
Cool. So what, they just, like, make the robot make a fist or something?
Actually, it's a little more interesting than that. They found that some of the strongest poses involve moving the robot arm through a series of singularities.
Singularities, what are those?
So a singularity is a point where the robot arm is like fully extended in a straight line. Like when you stretch your arm out as far as it can go.
Oh, okay. But wouldn't that make the robot, like, weaker?
You'd think so, right?
Yeah. Like if I try to lift something heavy with my arm all the way straight, it's way harder than if I keep my elbow bent.
Yeah, totally. But it turns out that by aligning the robot arm in a singularity, it can actually use its structure to support the weight.
Oh, really?
Yeah. It's kind of like how a weightlifter uses their skeletal structure to their advantage.
Oh, that's cool. So it's like the robot is doing a yoga pose or something.
Uh-huh. Yeah, kind of. And this approach actually reduces the amount of effort the motors have to exert.
Wow, that's so smart. Okay, so that's for strength.
Right.
What about speed? How do they make the robot move super fast?
For speed, they took inspiration from things like a trebuchet.
A trebuchet.
Yeah, or a badminton player's swing. It's all about storing energy and then whoosh, releasing it quickly.
Oh, I see. Like winding up a spring and then letting it go.
Exactly. So they designed a fast pose trajectory that involved a series of wind-up motions. The robot arm would like swing back and forth, storing energy in its joints,
Yeah.
and then release that energy super fast to get a high velocity.
I can just imagine this robot arm just like zipping through the air. How fast did it actually go?
Well, they got it up to a simulated linear velocity of approximately 4.4 meters per second.
Whoa, that's fast. Okay, so we have the strong robot and the fast robot. What about tasks that need both? Like something that's heavy A&D needs to be moved quickly.
That's where the blending of trajectories comes in.
Blending.
Yeah. They figured out a way to like combine elements of the strong and fast trajectories to make like a hybrid approach.
Oh, that's cool. So like a custom blend, depending on what the robot needs to do.
Exactly. It uses both the velocity and the force manipulability ellipses during the optimization process.
So it's finding like the sweet spot where the robot can be both strong enough and fast enough.
Yes, precisely.
Nice. Did it work?
Yeah, they tested it out, and it actually worked really well. They simulated a task where the robot arm had to lift a 6-kilogram payload and move it quickly to a target position.
Cool. And
The blended trajectory was faster than the strong trajectory, but it did require higher joint torques.
oh, okay. So there's like a trade-off there.
Right. It's like you can't always have the best of both worlds, you know?
Yeah, that makes sense. Okay, so this whole planning with purpose idea, did it actually like pan out?
Yeah, I think so. It showed that, like, by thinking about the specific task and using these manipulability ellipses,
Yeah,
you can design robot motions that are way more efficient.
that's awesome.
Yeah.
But like, is it really that easy?
Well, it's not exactly a walk in the park. There are definitely some challenges.
Like what?
One of the big ones is tuning the optimization parameters, like
Mhm.
finding the right balance between speed, strength, trajectory duration, all that stuff.
So it's not just like plug and play.
Right. It takes some expertise to get it just right.
That makes sense. But it sounds like the potential benefits are huge.
Definitely. I mean, this research could lead to robots that are way more adaptable, efficient, and capable.
Okay, so we've talked about the high-level planning, the strong and fast trajectories, the blending.
Yeah.
But like, how does this actually work in the real world? Like, how do these planned movements get turned into, actual movement?
That's a great question. And that's where the low-level control system comes in. Think of it like the conductor of an orchestra, making sure all the parts are working together in harmony.
Oh, okay. I'm listening. All right, so the low-level control system, that's what actually makes the robot move, right?
Exactly. It takes those high-level plans we've been talking about
Mhm.
and turns them into real-world motion.
So, like, it's the one actually telling the robot's motors what to do.
Yes. It's constantly monitoring the robot's state, comparing it to the planned trajectory.
So it's making sure the robot is, like, staying on course.
Right. And if the robot starts to deviate from the plan,
Oh.
the control system makes adjustments.
So it's like making those tiny course corrections.
Yeah, exactly. Now, the things that actually control the motors are called actuators.
Actuators.
Yeah, they're like the muscles of the robot. In this research, they use something called series elastic actuators.
Ooh, fancy.
Yeah, they provide really precise control over force and movement.
Nice. Okay, so we've got the high-level planner, the low-level controller, and the actuators,
Uh-huh.
all working together to make this robot move. Sounds pretty complicated.
It definitely can be. One of the biggest challenges is dealing with, the complexity of robot dynamics.
Robot dynamics.
Yeah, like all the physics and math that describe how a robot moves.
Oh, okay. I can imagine that gets pretty messy.
It does,
Yeah.
especially when you have, multiple joints and links all moving together.
Yeah, it's like not just moving one part at a time.
Right. You have to coordinate all of them to make a smooth, efficient movement.
Right, right. So how do they deal with that?
Well, they use a technique called feedback linearization.
Feedback linearization.
It's a way to basically compensate for those complexities and make the robot behave more predictably.
So it's like smoothing out the bumps in the road.
Yeah, that's a great analogy. And by combining that with those task-specific plans we were talking about,
Uh-huh.
they were able to get some pretty amazing results.
Yeah, this whole planning with purpose thing is really blowing my mind. So, like, what's the big takeaway here?
Well, I think it shows just how much progress is being made in robotics. We're starting to see robots that are way more adaptable and efficient, you know?
Yeah, and not just tools, but like partners.
Right. Robots that can work alongside us in all sorts of environments.
And it all started with like looking at how we move, right?
Exactly.
Yeah,
There's so much we can learn from the human body.
that's so cool. As we wrap up this deep dive, do you have like a final thought for our listeners?
Hmm. Well, this research was all about optimizing robot movements, but I think the ideas behind it,
Wow.
like planning with purpose and adapting to the task at hand,
Yeah.
those are ideas we can apply to like anything.
Oh, I see what you're
It
saying.
makes you think, you
Yeah.
know? Like,
Yeah.
how can we use those same principles in our own lives and the way we design things or approach challenges?
Yeah. Like maybe even the way we move our own bodies.
Mhm.
Wow, that's a great point. All right, everyone, that's it for this deep dive. Thanks for listening. We'll see you next time.